we are done with this power. Now we go to sequential logic, right? So in sequential logic, what is the sequential logic? I think probably you know, but we need to define it carefully also. Combinational logic is what? It's just combinational. You have a lot of logic inside, but it is very simple. It has nothing to do with time. The output is just a function of input. For example, C equal to AB dot. This is a NAND gate, right? So whatever you give me in AB, I will compute C. So that's a combinational logic. A sequential logic has something called state. To store, this is a storage element, right? Now we need to be careful. This storage, of course, can be anything, but what we're talking about is storage element on the CPU is very close to the operation, the logic. So it's not even the SRAM. We're talking about the register, right? I will explain more. But that is just a storage element right next to the combinational logic. What is the output? Definitely it's a function of the input. Okay, but it's also a function of the previous state. Okay, because when this comes in, yeah, it's affecting output. But at the same time, this one also take the output from the state. So this one will generate a new state, and then it will store here for the next clock cycle, right? So here we have the concept of time. But what is time? Time is the clock, right? If we are mechanical, we don't think about philosophy. Clock for our daily life, time for our daily life is just the clock on your iPhone or the clock on the wall. You see, it takes from 1 to 2 to 3. That is the clock, right? If we don't just operate mechanically. Same for this circuit. It has a clock. Every chip has a clock if it's a synchronous chip, right? So in every clock, we are going to do something. And that may update the state, right? And we take the output of that state, which store the value due to the previous state. And then we use it to compute the next state. So that is the sequential logic. So in a sequential logic, you will have a storage element, which is gated by the clock. Any questions? Yeah, and that's come to the so-called finite state machine, right? We have input, we have output, and then you will compute the next state. And then we have something called the register, and then it will copy to the current state. So this register is a little bit special. It's called positive edge trigger register. So what does it mean? It means when the clock change from 0 to 1, only when it change, D will be copied to Q. Okay, that's how it works. Okay, now we can look at a timing diagram. So this is T, and you have this signal. This is what I call the clock. You have the clock coming in, okay? And then you also have some data. Let's say the data is like this. Start from 0 and then 1 and then go back. This can be the data. The data appear here. Okay, and then what happened to Q? So according to the rule, when the clock goes from 0 to 1, we will copy. This is going from 0 to 1. This is going from 0 to 1. Okay, so whenever we see it goes from 0 to 1, we will copy. Copy. Here, copy, copy, right? So what do we get in the output? You will start, let's say you start from 0. Now you copy, you will go up. Then nothing will happen. Until here, you say copy again. Okay, I'm already 1. Yes, you did copy, but I'm still the same. And then I reach here, you say copy. Now the D is 0, so I go down. And here you copy again, right? So you see that it is only copy when the clock goes up, right? I'm going to talk more later, but any questions about this register?
Professor, in copy mode, so when D have to be in high position, right?
For D, no. For D, you always copy. You just copy whatever you have. So D can be at 0. For example, here, right? I need to label this is Q, right? So for example, here, the Q was at 1. But then when you copy, the D was 0, so it becomes 0. You see what I mean?
Okay, when does Q get disabled, Professor? Like when the clock goes from 1 to 0, does it not get disabled?
Correct. When it goes from 1 to 0, it does not copy for this type of register. I will say more. This is so-called edge trigger register. It only, there are other types. Some register, they will do copy even you are going down. But for the one I'm showing here, it only copy when you go from 0 to 1.
Okay, got it. Yes.
Good. Yeah. So this is a good question. We need to make this very clear, right? This class is very easy, I can tell you. It's just all the concept and terminology can confuse you. So make sure that everything is clear. You should be able to do a good job, right? So here it only copy when you go up, right? So let me talk about, so you see the memory is very important. So I would like to talk about classification of memory. They call it something called foreground. That is what we are doing here, is so-called register. These are actually some element right next to your logic, right? If any of you have done assembly language programming, you will know that sometimes we say add. I learned it maybe 20 years ago. I don't know if you learned that or not. I don't know the syntax anymore. Add R1, R2. You will say, take the R1 and R2 content, add them and put in R1. But where are these R1? They're called register, right? At my time, I was using 386. If I remember correctly, you might only have 16 register. That's it. You use this to do all the computation. These registers are super fast as your logic, but they don't have a lot. If you miss something, you need to copy from SRAM. You know SRAM is very fast already. They are on chip, but still not as fast as this register, right? So this is the fastest, the copy to the register. So this is what we're talking about here. So when you do pipeline design, we don't talk in this class, but all this sequential logic, we're talking about this register. They are not SRAM. Okay, that is the first thing. Okay, so here they say SRAM is high density. From your perspective, you might say, well, I thought SRAM is expensive. Yes, it's low density compared to DRAM, but however, it's very high density compared to register. Okay, so that is another level, right? Memory, I also want you to have this concept. Always remind yourself, when people talk about some memory, you go to a conference, in your meeting, your company meeting, someone pop up with a new memory. First, ask yourself, is it dynamic or static, right? They are going to tell you. Dynamic means what? You need to charge them periodically. For example, DRAM is a dynamic one. DRAM is a very simple device. It's actually just a pass gate transistor, and then with a capacitor, and this capacitor is a parasitic capacitor. You even don't build them deliberately. So you see, this is very dense. That's why you get DRAMs like in gigabytes and so cheap, right? But the problem is what? If I store a charge here, if you still remember what we talked before, this is just like a dynamic logic. This node is floating. If this transistor is off, they will leak away. So for DRAM, you need to refresh them every millisecond or whatever. I don't know the number, right? It's not just that it consumes memory. It's not just that it's volatile. Volatile means what? You turn off the power, the content is gone. This is volatile. But not just that. Even you put the VDD there, they will leak away eventually. You need to keep refreshing. That's why DRAM is troublesome in this way. But they are very dense. Okay, you need to charge them periodically. Some memory are static, and of course, register is static usually, right? For example, SRAM, which we'll discuss later. It is just a couple pair of the inverter, and then come up with a SS transistor. I won't go into detail, but you can see if this is 0, this has to be 1. They are bistable, right? Once I store left is 0, then I store the information. I don't need to refresh them because they keep regenerate. Of course, I need to turn on the power supply, VDD, right? So that is the difference between dynamic and static. Now, here we don't talk about clock gating. Clock gating is that something we try to save the energy. We try to not apply the clock to a certain block, right? And if that is the case, you cannot use dynamic because dynamic, you need to apply the clock to count it, to keep charging it. For static, then if you have clock gating, you don't apply the clock to a certain block at a certain time, then you definitely need the static memory. Okay. Now we also talk about long volatile memory before, right? Because this is my area in device, so I always say about that. But because this is so important nowadays, right? We talk about, of course, you know about flash memory is long volatile, very cheap, right? Very from SanDisk, Western Digital, Micron. What else do we have? We have this PCM. Phase change memory. I think I have article of the day talk about that earlier, that Micron quit the business and Intel is only exclusively using their cross point memory. They are long volatile. And I also have article of the day talk about the magnetic RAM. They are long volatile. They're very close to the SRAM in terms of speed. And that's cool. I can hold the whole block and turn it on immediately. Right? And of course, we have something called resistive memory. Hopefully, it will be useful in the future. Right? These are the long volatile memory. Right? It means that even I remove the VDD, the content are still there. Right? I spend so much time on this because I want to keep immerse you in the important terms. These are the terms that actually the concept, the notion you should have whenever you encounter a new memory or people start discussing memory. If you cannot categorize your memory based on this, it means you don't know what you're talking about. Once you categorize them, then you know how you can use them, whether they're fast, they're slow, what are the benefits. Okay, so these are some memory. But last thing I want to talk about is the difference between the latch and register. Okay, what is a latch? Now that related to what Sai just asked me, right? This one only go up, only copy when it go up, when it goes up, right? Some memory, it will copy whenever it reaches a certain level, okay? Not going up. It's not about the transition. It's not about the transition. So it's called level sensitive. I will explain more. Another is edge trigger, like what we're doing here, right? It copy when it changed the state. Okay. Okay, sorry. I think my internet connection was bad, right? Just now, I think I start lectures, right? Did I cover this part, lectures and register?
Yes, Professor.
Okay, so I was talking about the latch is just level sensitive. Whenever it's high or 0, then it copy. For register, it's edge trigger. Okay, and in this textbook, sometimes the free fall is mean by cross couple, but doesn't matter. The main point is this. If there's any ambiguity, you should ask the people who are talking to you, what are you talking about? You first make assumption, but when you reach the critical point, you make sure, right? That's about engineering, very important. Don't make any assumption. Just like when you're doing my project, right? You're so scared about the score, you don't make assumption, you come to me. Just like there was a student come to me to make sure, how come you didn't ask me to submit anything about QLC? It doesn't make sense at all. And indeed, it doesn't make sense, but indeed, I did not ask you, right? Because you care about your score, you will ask. Same when you go to work, you need to ask. Don't make any assumption. People won't praise you for not asking. Okay, they will only blame you when you did not ask and then did something what they don't want. Okay. So what is a latch? Latch, there are two types of latch. One is called positive latch. So what does it mean? It means when the clock is high, it's transparent. That's why we call it transparent high. So this type of latch we design it so that when clock is high, D will be copied to Q. Okay. And then when the clock is low, we say that it is in the whole state or whole mode. Okay, let's look at the timing diagram. This is the clock. This is the input data. So when the clock is low, even your data keep changing, nothing happens because you cut it, it's whole. Once the clock is high, you change your input data at D, yeah, it just change accordingly. And once your clock is low again, it just hold whatever the last value it has. That's why it's called transparent high. Similarly, you can design a latch, which is the opposite. When it is 1, it is in the whole mode. Okay, when the input is 1, it's in the whole mode. And then when the clock is 0, then it is transparent. And we also call it transparent low. When the clock is high, here is whole. When it is low, when your input is changing, it copy. When the clock is high again, even your input is changing, it just hold the last state that you copy, right? And continue. Okay, any questions? Pretty simple, right? Latch. But then we still have something called register or edge trigger register. That's on the left. What's the difference between the symbol? You have something like this. This means it's edge trigger. Let's look at it carefully, right? We just talked about latch. So let's take a look. When the clock is high, it just copy, keep copying. When the clock is high, copy. And do you see that here is copy? Once it becomes 0, it copy immediately. Right? It's just like that's why it's called latch. Like the gate. Once it's open, you have whatever you have here will go to the output. How about for the register? Then it will be different. This is positive edge trigger register. Again, it only copy when you go high. So here, when it go high, when it goes high, it copy. So it becomes 1, right? Now, this one changed to 0 now. You don't copy. Why? Because the clock is high, but it's not edge trigger. The whole region, even D is 0 up to here, it doesn't copy. Until it goes up again, copy. Any questions? Right? Maybe you think these are too simple. You learn in the old time already, which is true. Now then, our class not just this, right? Now we understand how it works, but then now we need to understand a few terminology, okay? So we say that it's going to copy for the edge trigger register, right? So when the clock goes up, it should copy. Now we should realize that the clock is not going to be perfect. It has a slope. So we only look at 50% point time. To successfully copy something, right? A data, right? We need to meet a few things. TSU, which what we call it the setup time. It means that the data need to be ready, TSU, before the clock. What does it mean? It means that if I want to copy this data to here, your data need to be stable for TSU. You cannot, it's just like you cannot do things in the last minute. Because of the mechanism we're going to discuss, we're going to calculate the TSU, right? But you need to be stable for TSU unit, the setup unit, right? Second, you also need to fulfill the whole time. The data need to be stable T-hole after the clock. Okay, so once the clock come out, you do not think that I already got the data. You need to hold for another amount of time. But this can be zero. TSU can be zero also. But just that in general, you have this definition. TSU, setup time and hold time. You need to fulfill it within this period. Data has to be stable. Otherwise, I cannot copy the data. I'm going to do something wrong. Okay. And then another quantity we always see is TCQ. TCQ means clock to Q. It means that do not expect me to copy immediately. It's just like the bureaucracy in some organization. Okay, you give me the data, it takes me TCQ to be available. So don't copy, don't think that I'm ready at this time and take the data for computation. Wait for at least TCQ before you take the Q for computation. Is this okay? The best is to give some examples in numbers, right? For example, this one can be 2 nanoseconds. Okay, and this can be 1 nanosecond. And let's say this is 3 nanoseconds. Right, the criteria. Let's say I give you a chip, right? We say the setup time is need to be 2 nanoseconds, the whole time is 1 nanosecond, and the TCQ is 3 nanoseconds, right? So what does it mean? It basically is saying that, okay, if my pulse come in here, let's say this is 0 nanosecond, I go up, I need to wait for 2 nanoseconds. I need at least to wait for 2 nanoseconds before the clock comes in. This is 2 nanoseconds. This is the clock. Okay, I'm copy at 2 nanoseconds. And then it takes 3 nanoseconds to appear here. So it may like the data output would be 5 nanoseconds, right? So at 2 nanoseconds, my clock comes in, the data is ready at 5 nanoseconds. Of course, it can be earlier, depends on the data type. But what we guarantee is that 5 nanoseconds. Don't come here 3 nanoseconds before 3 nanoseconds, after 2 nanoseconds, okay? Or before 5 nanoseconds, right? And Then you can go down. Maybe I don't need to put this one. And if you have some new data, you don't change it before 3 nanoseconds. Otherwise, I won't be able to copy it successfully. So you need to be ready for 2 nanoseconds and 1 nanosecond here. And my clock come at 2 nanoseconds. The clock data will be ready in 5 nanoseconds. Okay. Any questions? Is that clear?
Yes, sir.
Thank you. Now it becomes more complicated. Okay, so we know all those matrices. Now I introduce another two terminology. One is called T logic. Okay, so this is easy. This is the worst case delay when you go from left to right, right? So what all you are doing in the adder, right, is the worst case delay. Let's say you find T sum or T carry, whatever, you measure it, right? It takes how much time to go from left to right? That is one thing, right? But there's also one thing called contamination delay. This one you may get unhappy. You know, being too fast is also a problem. I also need to know how fast, what is the fastest speed that the data will be copied from here to here. It cannot be copied too fast. If you do it too fast, you are going to screw up the circuit due to some reason we are going to explain. Okay, so contamination delay can be the contamination delay of the logic or the contamination delay of the register. So we say that the clock, the input come here or current state come here, right? Maybe it will start at, let's say 0 second, it change, 0 nanosecond, okay? And then it propagates all the way to here, right? That is the so-called T propagation logic, right? For example, I give an example, let's say 2 nanoseconds. So after 2 nanoseconds, the output is ready, which is good, right? But it also means that here, this is 2 nanoseconds, right? This one is ready, okay? Now, and then the clock comes in, then it's going to, but before the clock comes in, I need to have a setup, right? T setup. I need to make it stable before the clock can come in, right? So let's say the T setup is 1 nanosecond. So because of this, my clock come in at 3 nanoseconds, right? And then how long? Maybe it takes 2 nanoseconds to propagate. Let's say TCQ equal to 2 nanoseconds. Then this one will propagate. Let's say this one is doing some inversion. Then this becomes 5 nanoseconds, right? So what is the loop going through? It is 5 nanoseconds to go over this loop, right? This register mandate me to obey the setup time and clock to Q. Holding, we'll discuss later. Let's say assume it's holding correctly. So going through a loop is 5 nanoseconds. Then it means my clock cannot have a period shorter than 5 nanoseconds, right? So that's why the period has to be larger than this TP logic plus T setup, because I need to wait for so much to copy, so it will be ready, right? And then you take another TCQ 2 seconds, right? So because of this, then what is my frequency? The frequency is going to less than 1/5 nanosecond. And what is 1/5? This is like 200 megahertz. So this setup prevents you from running the clock faster than 200 megahertz. Is this clear? Everything okay? I know it might not be clear, right? We need to keep doing exercise later, right? Because if clear, then everyone get 100% in the final. Now you might see something already. What if I have certain input pattern? It goes very fast. Now, once I copy to here, what if this one has a contamination delay of, let's say, what should I put? I actually don't have an answer, but let's say this is like 0.5 nanosecond. Okay, let's say now you already know that when we talk about the delay, it's all about the worst case, right? When we calculate. But you also know some pattern will give you faster delay, right? Remember when you do the sizing, it is possible, or in the midterm, possible you turn on all the transistor and then they discharge the capacitor at the same time. So delay can be very fast for certain pattern, right? And this one can be the contamination delay, right? This is TCD logic. Let's say you can do it in 0.5 nanosecond. Okay. And similarly, let's say this one comes in, right? After setup, and then the clock goes up. And then this one can go through very quickly in some certain situation, CD register. Let's say 0.3 nanosecond. Okay, then in this case, there will be a problem. I copy this one after 0.3 nanosecond, and then it propagates to there after another 0.85 nanosecond. So it becomes 0.8 nanosecond. But this one requests a whole time. Right? I may request a whole time equal to 1 nanosecond just because of the requirement. We say that when the clock goes up, this one need to stay for 1 nanosecond. But however, this data goes so fast that it come back already and damage my data. I cannot hold for 1 nanosecond. Then I won't be able to copy successfully. The whole logic screw up. Right? So basically what I'm saying, when the clock goes up, D should not change for whole time. D should not change for whole time. But because of the contamination delay, this is so fast. Once it go up, it take only 0.3 nanosecond, and then you go through the combinational logic for 0.5 nanosecond. So this has not hold for 1 nanosecond, and then you fail. So that's why another criteria is your hold time has to be less than the contamination delay, right? So you cannot be too fast for your logic. That is another problem. Okay. This may be confusing, right? Think about that and let me know you have any questions. Any questions? Clear? Okay, if it's clear, then let's move to, I just want to review again the bistable elements, right? So now we talk about the ratchet. So we see the big